So, very good afternoon to all. Today I am taking the class of electrostatic field and electromagnetic field for the gate purpose. So, in that electrostatic or electromagnetic fields, that is EMF, electromagnetic field theory. Okay, in that one, the topics are Maxwell equations, propagations, transmission lines, and waveguides. Okay, in that Maxwell equations, so today we discuss about these Maxwell equations and boundary conditions. So now Maxwell equations. Maxwell equations. Now, for any electromagnetic waves, while transmission from one medium to another medium or through the homogeneous medium, now the waves can be propagating to the free space medium or dielectric medium or conducting mediums. These waves must satisfy the Maxwell equations. These Maxwell equations can consist defined on both electrostatic and electromagnetic fields. So both electrostatic and magnetic fields. Now these Maxwell equations can be defined based on the time varying fields, time varying fields, and next one is static fields, static fields, and third one is time varying field for free space, for free space. Just 1 minute. Now, in the time varying field, the time is changes, that is the parameter it changes with respect to the time, that is the electrostatic, that is the electric field intensity E or electric flux density D or magnetic field intensity H or magnetic flux density B. These are all the parameters, that is nothing but E value, D, H and B. Electric field intensity, electric field density, magnetic field intensity, magnetic flux density. These four parameters it changes with respect to the time. Then that is the time varying fields, and these four parameters are stationary with respect to the time. Then that is called as static fields. Whereas in the time varying field for free space, then the constant values epsilon r is equals to 1 and mu of our permeable relative permittivity and relative permeability is equals to 1. Just we can considering only absolute permittivity and absolute permeability. Okay. Now first we'll see what is the Maxwell equations. Maxwell equations for time varying field. This time These Maxwell equations you can representing in two different ways. That is the differential form and integral forms. Now, and also, so differential form and integral forms. And integral forms. Now, and another thing is these four parameters considered while defining the Maxwell equations based on dot product and scalar product. Now, the first Maxwell equations is equals to del cross E is equals to minus dou B by dou T. Whereas in terms of integral form, integrals of E into d of L is equals to minus of integral of dou B by dou T into d of S. This equation we can call it as Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. Okay. So the meaning, the word statement of this equation is nothing but the electromotive force, that is the EMF, that is integral of E is the electromotive force, EMF around a closed path. This is the closed path, integral of closed integrals around the closed path is equals to negative. Here it is sign is negative. Negative of surface integral, this is surface integral of S with respect to d of S. Surface integral of rate of change of magnetic flux density over the closed surface. That is, so the electromotive force around the closed path is equals to the negative of negative or surface integrals of rate of change of magnetic flux density over the surface bounded by the closed path. That is the meaning of this mathematical function of Maxwell equations of time varying field in Faraday's laws of electromagnetic induction. Next, the second equation is del cross H is equals to J plus dou D by dou T. Now, then this is the form of differential form, and in terms of integral forms, integral of H into D of L is equals to integral of J plus dou D by dou T into D of S. This equation we can call it as Ampere's circuit law. Ampere's circuit law. Ampere's circuit law. That is nothing but this equation is representing as the magnetomotive force H. Here it is E is nothing but electromotive force. In the second equation, in terms of Ampere circuit law, H is indicating the magnetomotive force of the closed integrals is equals to sum of the current density, surface integrals of sum of the current density and displacement current over the surface bounded by the closed path. So once again I tell you, The magnetomotive force MMF around the closed path is equals to the surface integrals of the sum of conduction current density and displacement current density. Okay. Current density is J and displacement current is dou d by dou t over the surface bounded by the closed path. This is nothing but Ampere's circuit law. And third Maxwell equation of time varying field del dot d is equals to rho v, or integral of d into d of s is equals to integral of rho v into v. This equation we can call it as Gauss law of electrostatic. Gauss law of electrostatic. That is nothing but the total electric flux density passing through any closed surface is equals to the total charge in the volume enclosed by the closed surface. Okay. The total electric flux passing through any closed surface is equals to the total charge in the volume enclosed by the closed surface. And the fourth equation of Maxwell equations in time varying field del dot B is equals to 0 is in the form of differential form, whereas in integral of b into d of s closed surface is equals to 0 in integral form. That is the net or total magnetic flux density for the closed surface is equals to 0. This equation we can call it as Gauss law of magnetostatics. These four equations we can call it as a Maxwell equations for time varying fields. Next, what are the Maxwell equations of static fields? That is nothing but in the static field there is no rate of changes with respect to the time. That is, it is always constant. There is no, that is independent. The Maxwell equations is independent of time. Independent of time. See the first equation while comparing this differential form. This dou b by dou t is equals to 0 in the static fields. Because of the static field is nothing but that is independent of time. It is, there is no changes with respect to time. Okay, so this equation is equals to 0, and the second equation del cross h is equal to j plus dou d by dou t, rate of change of flux density with respect to time. This term is also equals to 0. So these two terms is equals to zeros. Therefore, the Maxwell equations for static field the Maxwell equations for static fields here also can defining both differential forms and integral forms. Differential form and integral forms. So first equation del cross E is equals to 0. Integral of E into d of L is equals to 0. This is nothing but Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. And the second equation, del cross H is equals to Z. And the integral of H into d of L is equals to integral of J into d of S. This is Ampere circuit law. And third equation, del dot D is equals to rho V. In terms of integral form, integral of del dot D of S is equals to integral of rho V into D of V. This is Gauss law of electrostatic fields. And fourth one is del cross B is equals to 0. That is integral of B into D of S is equals to 0. This is Gauss law of magnetostatics. Now we can comparing the previous equations and these equations of both time varying and static fields. Here all are independent of t. There is no time variations. See the first equation, del cross E is equals to generally minus dou B by dou T. That is magnetic flux density with respect to the time. But in the static, it is a constant value, then that is equals to 0. So therefore, integral of E into d of L is equals to 0. The total electric field, the EMF enclosed by the closed path is equals to 0. That is the Faraday's laws of electromagnetic induction in static fields. The second equation, del cross H is equals to J plus dou D by dou T. So dou D by dou T is a constant in terms of static fields, and it is varies in terms of time varying field. So the equation can be rewritten as del cross H is equal to simply J, that is current density. In terms of integral form, integral of H into d of L is equal to integral of J. The MMF enclosed by the closed path is equals to surface integrals of current density. That is nothing but Ampere circuit law. And third equation, del third and fourth, that is del dot D is equals to rho V and del dot B is equals to 0. These two equations are similar to Maxwell equations of time varying fields. Next, Maxwell equations of time varying field. Maxwell equations for time varying field. Time varying field of free space. Of free space. Now, here also can defining in two forms, that is differential form and integral forms. So here also differential form and integral forms. The first equation, del cross E is equals to minus dou B by dou T. That is equal to integral of E into d of L is equals to surface into closed path. Dou by dou T of integral of B into d of S minus. This is same thing, Faraday's laws of electromagnetic induction. And second equation, del cross H is equals to minus dou d by dou t. So integral of h into d of L is equals to integral of dou d by dou t into d of s. This is Ampere's circuit law. And third equation, delta d is equals to 0. That is integral of d into d of s is equals to 0. This is Gauss law of electrostatic. And fourth one, del dot b is equals to 0. It is integral of b into d of s is equals to 0. This is Gauss law of magnetostatics. Magnetostatics. So this is the equations of Maxwell for different fields like time varying field, static fields, and time varying field of free space medium. Okay. Next, now all these components, that is the Maxwell equations of different fields, either time varying field or time varying field in free space medium or static fields, all the field components of Maxwell equations defining based on the homogeneous medium. Homogeneous medium, that is the single medium. If the waves is electromagnetic waves are transmitted from one medium to the another medium, that is either free space medium or air medium or dielectric medium or conducting medium, that is the electromagnetic waves are transmitted from one medium to the another medium, how these Maxwell equations will be affected. What are the boundary conditions of electromagnetic fields when the waves is transmitted from one medium to the another medium, and how these waves can satisfying the Maxwell equations. What will be the effect of waves when crossing the boundary or while interfacing the different mediums? That is nothing but boundary conditions of electromagnetic fields. So the next topic, boundary conditions. Boundary conditions of electromagnetic fields, EMF. Boundary conditions of electromagnetic fields. Now, so far we have considered the existence of electric fields in homogeneous medium. Homogeneous is nothing but the similar, same medium. If we can change the medium from one medium to the another medium, the mediums is free space medium, that is the air medium, conducting medium, dielectric medium, and dielectric and conductor and free space. Up to now, we'll see only the one mediums. Now, if the field existing in a region consisting of two different media, the media is different. Now, the conditions that the field must satisfy at the interface separately, the medium is called as a boundary conditions. The conditions that the field must satisfy at the interface separating the media are called boundary conditions. These conditions are helpful in determining the field components on one side of the boundary if the field on the other side is known. So one side of the field is known, then what about the effect of the electromagnetic fields? Either electric fields or magnetic fields in the other side when the wave is crossing the boundary or the waves is connecting or interfacing between the two different mediums. Now the boundary conditions are in the interface separating by dielectric, dielectric, that is epsilon R1 and dielectric epsilon R2, and second one is conductors and dielectric. Conductors and dielectric. And third one is conductor and free space. Conductors and free space. Class lo unna papa? Class lo unnanu? Pedtale. Okay. Conductors and free space. Okay. Now the first one is now to discuss about the first thing. Now, before going to discuss about these boundary conditions, to determine these boundary conditions while using the Maxwell equations. So, what are the Maxwell equations can satisfying these boundary conditions? How these boundary conditions can satisfy the boundary conditions. So which equation can satisfy the boundary conditions of Maxwell equations? Now, so we'll consider the static fields of Maxwell equations. Integral of E into d of L is equals to 0 in the integral form, or del cross E is equals to generally minus dou B by dou T in that case of time varying field. Whereas in the static field, del cross E is equals to 0 in differential form, whereas in the integral form, integral of E into d of L is equals to 0. This is one equation, and corresponding density functions integral of d into d of s is equals to qn close. This q enclosed is nothing but free charge enclosed by the surface. Free charge enclosed by the surface. Also, the electric field intensity. So, the electric field intensity E into two orthogonal components. That is nothing but the electric field intensity E cap or E bar vector component has two orthogonal components. Has two orthogonal components. That is E is equals to E of t plus E of n, where E of t is nothing but tangential component, and E of n is normal component. Tangential component and normal component. The same procedure we can using for flux density, because d is equals to epsilon into E value. If d of t tangential component of flux density dt is equal to epsilon into E of t, or d of n is equals to epsilon into E of n, where epsilon is equals to epsilon naught into epsilon r, where epsilon naught is nothing but absolute permittivity and epsilon r is relative permittivity. Now, now, any boundary conditions, that is dielectric to dielectric or conductor to dielectric or conductor to free space, any boundary conditions, any boundaries between these can satisfy this Maxwell equations. Now, see the first concept of boundary conditions: dielectric, 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 dielectric boundary conditions. Boundary conditions. Now, we will consider any boundaries condition. Boundaries. This is E of 1t tangential component. This is the natural normal component. This is electric field component of first medium. E of 2t E of 2 E of 2n. This is the first medium. This is the second medium. First medium permittivity is epsilon 1. This is epsilon 2. and any closed surface or this dielectric medium, just I'll change. So A, B, C, D. This length is del of omega and height is del of h, del of h. Now here, so consider from this diagram, consider the electric field E existing in a region that consists of two different dielectric characteristics. Two different dielectric characteristics. Characteristics here it is, that is the permittivity constant epsilon 1 and epsilon 2, where epsilon 1 is epsilon naught into epsilon r1 and epsilon 2 is equals to epsilon naught into epsilon r2. Okay. Where epsilon naught is absolute permittivity, that is the constant value, and epsilon r1 is the relative permittivity that depends upon the material what we use in the medium. If it is a conducting medium, that relative permittivity is depends upon the what material we can use for that conductor. There are aluminum or silver, copper, like that. Now, the field components E1 and E2. E1 is the first dielectric medium and E2 is the second dielectric medium, and this is the boundary. When the waves is crossing from this bond electric medium 1 to medium 2, what will be the effect of electric field components E1 and E2? Now, these fields E1 and E2 can be decomposed in tangential and normal components. So E of 1 is equals to vector components. E of 1t plus E of 1n. Similarly, E of 2 is equals to E of 2t plus E of 2n. So the electric field components of both tangential and normal components. Now, as we know that the potentials of any closed path is zero, that is integrals of E into d of L is equals to 0. So the potential or electric field for the any closed path is equals to 0. This is the Maxwell equation. Now we have to verify that these dielectric boundary conditions in satisfying this equation. Okay. So here the electric fields is E1 and E2, and the closed path is here this closed path A, B, C, D, E. This is the closed surface, closed path. It is A with length is del of omega, and BC with the height is del of H, CD and DA. This is the closed surface. Now, We have to applying this function in this closed surface, then what is the electric field or total potential? That must be equal to 0. Now first we will start from starting point A. From A to B, what is the electric field? This is the corresponding, this is tangential component F1t into what is the length of this A to B? Del of omega plus from B to C. B to C is the component is normal component F1n into out of this BC, half of the height is in the first dielectric medium and second half is in the second dielectric medium. So in the first, and the current is passing through this medium is this one, clockwise. So the first half length is in the first medium and the second half is in the second medium. So this one is E of 1n into del of h by 2 plus, and the second half is in 2n into del of h by 2 plus from C to D. C to D is opposite direction. C to D, but E of 2t is in this direction. This is nothing but a tangential component in the medium 2. So it will comes opposite direction negative. E of 2t into del of omega with length is del of omega plus from D to A. D to A again half is in the second dielectric medium and another half is in the first dielectric medium. These two, this is nothing but the natural normal component. So E of 2n into del of h by 2 plus E of 1n into del of h by 2 is equals to 0. That is total potential or total electric field is equals to 0. Now in this equation, if del of h tends to 0, so the width of this conductor or width of that circular loop is equals to 0, then this equation becomes E of 1t into del of omega plus this term is equals to 0 plus this term is equals to 0 minus E of 2t into del of omega plus E of 2 into del of h by 2, del of h tends to 0. So 0 plus, and this term is also equals to 0 is equals to 0. Therefore, E of 1t into del of omega minus E of 2t into del of omega is equals to 0. Therefore, E of 1t is equals to E of 2t. That is vector. Therefore, the tangential component of E are the same on the two sides of boundaries, that is E1 and E2. So the E of t, vector component of E of t undergoes no change on the boundary and it is said to be continuous across the boundary. Since now from this potential, now we have to find out the flux density. D is equals to epsilon into E. where D is also representing tangential component plus normal component. Then from this equation, E of 1t is equals to d of 1t by epsilon 1. Similarly, E of 2t is equals to d of 2t by epsilon 2. Therefore, E1 of t is equals to, that is the electric tangential component of first dielectric medium is equals to E of 2t from the previous equation. So already as we know that E of 1t is equals to E of 2t. Therefore, d1t by epsilon 1 is equals to d2t by epsilon 2. This is the equation of dielectric flux density of the electric fields. Now the dt undergoes some change across the interface, since how it will change this, because for the electric field intensity there is no change. Whatever the electric field produced in the dielectric medium 1 is same as in dielectric field 2, but the flux density dt must undergo some changes. That is nothing but discontinuities across the interface, because as we know the equations, integral of d into d of s is equals to surface integrals of d into d of s is equal to qn close, qn close. In cylindrical Gaussian, then del of q is equals to rho of s into del of s. That is nothing but that is equals to d1n of del of s is minus d2n into del of s. Therefore, or d1n minus d2n is equals to this del of s. Here this del of s is cancelled. Therefore, rho into f. This is nothing but, this row of S is nothing but free charge density. Free charge density. Now, if there is no charge, if there is no charge density, okay, if no charge density, then rho of S is equals to 0. Therefore, d1n is equals to d2n. So this is the equations, that is previous case, this equation and this equations and this equation are called boundary conditions, and they must be satisfied by the electric field at the boundary separating by two different dielectrics. Okay. Next, second one. Second, conductor dielectric boundary conditions. Boundary conditions. Next, now first we have to draw the boundary condition between the two. So this is the so this is the resultant field E of n, E of t, tangential component, normal component. Here the permittivity is epsilon and medium 1. This is conductor E is equals to 0. Now in a closed path, this is A, this is B, this is C, this is T, and length is del of omega and height is del of h. Now here it is. From this diagram, the conductor, first we have to assume that the conductor is a perfect conductor, that is the conductivity is equals to infinity, and or rho is equals to 0. So the conductor is assumed to be this one. The conductor is assumed to be a perfect conductor. Then the conductivity is equals to infinity. So the material used for satisfying this condition, sigma is equals to infinity or rho is equals to 0, is copper and silver. Copper or silver. Copper or silver are used for a perfect conductors. Now we have to determine the boundary conditions for a conductor and dielectric. Conductor is the first medium and dielectric is the second medium. So to determine the boundary conditions for a conductor and this conductor dielectric boundary conditions also satisfies the Maxwell equation integral of E into d of L is equals to 0. For a closed path, for a closed path, A, B, C, D, A. That is A, B, C, D, and A. Now, first we have to applying this condition. Total electric field intensity is equals to 0 or total potential difference about this closed path is equals to 0. Now we have to start here at the point of A. From A to B, the electric field is 0. So 0 into del of omega plus from B to C. So the current direction is A to B, B to C, C to A, D to A. So A to B, the conductor, the electric potential is 0. From B to C, again the half is in the conductor medium and the half is in the dielectric medium. So in the first half, it is equals to 0. So 0 into del of h by 2 plus, and the second half, it is a normal component, that is this half is similar to E of n into del of h by 2 minus minus means the loop is passing from C to D, but electric field is in this direction. So minus E of t into del of omega length, and minus this is in the downward and this one component is in the upward. So minus E of n into del of h by 2 plus 0 into del of h by 2. Second half is 0 is equals to 0. That is integral of d of L is equals to 0. Now here also same thing we can apply. If del of h tends to 0, so this first term is 0 plus second term 0 and anything is 0 plus this term is equals to 0 minus E of t into del of omega minus 0 plus 0 is equals to 0. Therefore, E of t is equals to 0. Similarly, so here the total electric field components, that is tangential component of the electric field is equals to 0. Similarly, the remaining boundary conditions can also be obtained. D of t is equal to epsilon into E of t. Okay? That is d of t by epsilon, that is d of t by epsilon is equals to 0. That is one equation. And a normal component epsilon into E of n is equals to d of n. Then d of n is equals to 0 because of E of n is also equals to 0. And this is also equals to 0. So this is the conditions of both electric field and electric field intensity and electric flux density for a medium is conductor and electric boundary conditions. So these three equations, that is E of t is equals to 0 and dt by epsilon is equals to 0 and d of n is equals to 0. These three equations must satisfy the boundaries for a conductor dielectric medium in which the conductor was assumed as a perfect conductor, that is inside the conductor E is equals to 0. Okay. Now, so I can conclude that for the today's session, first we have to explain the Maxwell equations of different field components, that is time varying fields, static field, time varying field for free space medium. In the time varying fields, del cross E is equals to minus dou B by dou T, that is in terms of differential forms, that is the total electromagnetic force EMF of a closed loop is equals to the surface integrals of negative of the rate of change of flux density in a closed path. That is nothing but integral of E into d of L is equals to minus of integral of dou B by dou T. And the second Maxwell equation, this Maxwell equation is called as a Faraday's laws of electromagnetic induction. And in the second Maxwell equation called as the Ampere circuit law is the magnetomotive force MMF of a closed integral is equals to the surface integrals of sum of the current density and displacement current over the closed path. And the third equation of Maxwell equation is called as a Gauss law of Integral of d into d of s is equal to integral of rho v into dv. That is the net flux density over a closed surface is equals to the total charge enclosed, total charge of the volume enclosed by the closed surface. And the last, Gaussian law of magnetomotive, Gaussian law of magnetic fields, integral of B into D of S is equals to 0. The net magnetic flux density over the closed surface is equals to 0. Now, these are all the equations are defining based on homogeneous medium. If the medium it changes when the waves is traveling from one medium to another medium, then it is not considered as a homogeneous. Non-homogeneous, that is one medium to the another medium. Here the medium it changes, then what will be the effect of Maxwell equations while the EM waves is traveling from one medium to the another medium? Now, these Maxwell equations can satisfying when the medium is in the boundaries or interfacing from one medium to the other medium. The boundary conditions are dielectric medium and dielectric medium, conductor and dielectric medium, conductor and free space medium. Now, in dielectric and dielectric mediums, this is the dielectric and dielectric medium. The electric field intensity of the first medium and electric field intensity in the second medium, E of 1t is equals to E of 2t. So the electric field intensity of first medium and second medium does not change. Whereas in the flux density, D is also not changes. That is enclosed by the path surface. And the second thing is conductor and dielectric boundary conditions. While considering the conductor, first of all, the conductor is a perfect conductor, the medium is a perfect conductor, then the conductivity sigma is equals to 0. Sorry, sigma is equal to infinity. The material used for a perfect conductor is copper and silver. Then we have to applying these Maxwell equations. Integral of A into D of L is equals to 0 for a closed path of A, B, C, D. Now we can applying the Maxwell equations for these equations. Then the closed path is equals to this equation, that is E of T is equals to 0. Therefore, the magnetic flux density dt by epsilon is equals to 0 and normal component E of n is equals to 0. This is the conclusion of the today's class.